Lesson 4.1, Impulse and Momentum. Often the force acting on an object is not constant. Think of a baseball or tennis ball being hit. When you first start to make contact, when you're barely touching, the force is very, very, very small because you're just barely touching. Then in the middle of the swing, the force is very, very high because you may have lots and lots of contact, really pushing the ball. And then as the ball is leaving, it's barely touching anymore. And so you have no force. So the force isn't contact. But the times of force are often short. But those forces can be huge. So we often talk about average force. So to hit a ball well, both the size of the force and the time of contact are important. So both of these are brought together into the concept of impulse. Impulse is force times the time. So J is the impulse, force of the contact. Technically, we're going to think about average force. And delta T is the time of the contact. Since the force is measured in newtons, time is in seconds, the unit for impulse is a newton second. And since force is a vector, impulse is also a vector. The direction matters. Object responds to the amount of impulse. A large impulse means there's a large response and a higher final velocity. A large mass, though, means there's less velocity. So both mass and velocity play a role in how the object responds to impulse. Which brings us to the idea of momentum. Linear momentum is P equals mv. P is the momentum, m is the mass, v is the velocity. So momentum is mass times velocity. Mass is in kilograms, and velocity is in meters per second. So the unit is kilogram meters per second. Since velocity is a vector, momentum is also a vector. And momentum is important when we talk about collisions. We haven't talked about collisions yet, so momentum is now the unit where it's just collisions. Now here's something interesting. So if I take the newton second of impulse, a newton is a kilogram meter per second squared because F equals ma. And times a second, one of those cancels and you're left with kilogram meters per second. So momentum and impulse actually have the same fundamental units. Let's derive the formula. F equals ma. That's Newton's second law. A equals change in velocity over time. It's the definition of acceleration. So if I take that and substitute it for the acceleration, I get F equals the change in velocity over time times the mass. If I distribute the mass, I get mvf minus mv0 over time. Multiply both sides by our time, and I get ft equals mvf minus mv0. So I get impulse equals our change in momentum. Impulse equals change in momentum. Impulse is change in momentum. That is the impulse momentum theorem. It's hard to measure the force during contact, but we could easily find the change in momentum. So we use our impulse momentum theorem and the time of the contact, because you can measure that fairly easily, and then use that to calculate the average force of the contact. A baseball, mass 0.14 kilograms, with initial velocity of negative 40 meters per second is hit. It leaves the bat with a velocity of 60 meters per second after 0.001 seconds. What is the average net force applied to the ball by the bat? So, first of all, why are the velocities different signs? Because initially the ball is going that way. After it's hit, the ball is going that way. Since they're going opposite directions, they have opposite signs. So impulse is force times our change in time, but I don't know the force. But that does equal our final momentum minus our initial momentum. So our mass is 0.14 kilograms. Final velocity is 60. Mass is 0.14 kilograms. Initial velocity is negative 40 meters per second. And so that gives us 14 kilograms meters per second. So our impulse, that is the impulse. Now if I put in the time, we can find the average force. So we divide, and our average force comes out to be 14,000 newtons, which is a rather large force. But you are hitting a baseball with a bat. A raindrop with a mass of 0.001 kilogram hits the roof of a car at negative 15 meters per second. After it hits, it splatters, so the effective final velocity is 0. The time of the impact is 0.01 seconds. What is the average force? Well, so our time is 0.01 seconds. Our mass, which is rather small because it's a raindrop. Final velocity is 0. Initial velocity is negative 15 meters per second. So that gives me negative 0.015 kilogram meters per second. It's positive because we have negative times negative. And then we divide, and that gives us 1.5 newtons, which doesn't seem like much force, but remember, it's just a raindrop. But what if it's ice, so it bounces off at 10 meters per second? All right, let's do the same thing. Now, I'm going to bet that with ice, like a little hailstone, is going to have a shorter collision time. Well, let's assume that it's the same collision time. I'm going to bet that a hailstone has more mass than a raindrop too. But we're going to say it's the same. Bounces off at 10 meters per second. The same initial velocity. This is 0.025 kilogram meters per second. Divide, and you get 2.5 newtons. So the effect of it bouncing off and not just hitting and stopping, the bouncing back actually increases the force because there's now a greater change in momentum, so a greater impulse.